How are you doing? Have you given up on the semester quite yet? You shouldn't give up on the semester because you don't want to be in school forever like me. So keep working hard and don't give up. You'll be fine in the end. So we begin with our first problem. We want to use Warshaw's algorithm to find a transitive closure. And what exactly does that mean? Well, we have a relation here, and we're given this set over here, 1, 2, 3, 4. And I think the first step we want to do in writing on this problem, like on homework or whatever, is we want to turn this into a matrix. So because it's going to be a 4x4 matrix, there are 4 elements, we make a matrix that can fit 4x4 grid. We have that 1 points to 2, so down 1 across 2, and a relation exists there. We have 2, 1, so down 2 across 1, 2, 3, 3, 4, 4, 1, and the rest are zeros because the relationship doesn't exist on those nodes. Okay, so you can see just perfectly fine. Okay, so the rest are zeros because a relationship doesn't exist on those pairings. So from there, this is our original matrix. We're going to run Warshaw's algorithm once, and we're going to get an updated matrix out of it. And how do we get an updated matrix? Well, on the first loop, we compare the first column and the second column. So looking at the first column and looking at the first row, we're going to look for every time 2 1s intersect. So for example, here we have a 1 in our column and a 1 in our row. They intersect right here at a 0, 2, 2. We are going to turn that 0 into a 1. In essence, we're creating a transitive relation that does not exist. So this 0 is going to become a 1 in our updated matrix. We also see that a 1 here on the first column, and again the same 1 on the first row, intersect at a 0. Let's update this 0 in our updated matrix. This will become a 1 as well. The rest don't change, right? So this 0 and this 1 intersect at a 0, but that doesn't matter. They both need to be 1s for us to update the intersection to a 1. What exactly does it mean to be adding a transitive relation? I think it's best illustrated with a digraph. So let's take our original matrix and turn it into a digraph. It's going to have 4 elements because we have 4 elements in our set. So let's create 4 nodes. Now let's draw arrows to depict relations. We have 1 and 2, so 1 points to 2. We have 2 and 1, so 2 points to 1. 2 and 3, 3 and 4, and 4 to 1. Now, a transitive relation is basically when, for example, 2 points to 3 and 3 points to 4. Doesn't that just mean that 2 points to 4? We're cutting out the middleman in a sense. So for example, after our first loop, we discovered 2 new transitive edges. 2, 2 and 4, 2 as well. Let's look at it at a digraph. We added 2, 2 because we have that 2 points to 1 and 1 points to 2. Why don't we just cut out the middleman? Let's cut out the 1 and simply say that 2 points back to itself. So after our first loop, we added an edge from 2 back to itself. We also added the pairing 4, 2, right? A new transitive edge. We added it because we have the relation 2 to 3, we have the edge 4 to 1, and we have the relationship 1 to 2. We have that 4 goes to 2 through 1. Let's just cut out the 1, cut out the middleman. Let's simply say that 4 points to 2 directly, right? And that's all we're doing. We're repeatedly adding edges to depict a new transitive relation. So we've updated our matrix, and we're going to use the new pairings to see if those new pairings lead to even newer transitive relations. All right, so we go on to the next loop. Let's say that this is after k equal to 2 loops. All right, I'm going to copy down this previous matrix, and I'm going to look at the previous matrix right over here, and we're going to look at the second column and the second row. We have a 1 and a 1 here that intersect at a 0. Let's turn that 0 into a 1 in our updated matrix. Again, a 1 and a 1 intersecting at a 0. A 1 and a 1 intersecting at the top right corner. And I believe that is everything we can find on that iteration. Now, whenever we're dealing with whatever current column or row we're dealing with, so we're dealing with row 2, column 2, we never update the values in those particular rows or columns. So on the next loop, maybe we can update something on them, but on our current loop, we can never update anything in the column and anything in the current row. Okay, so now we go on to the next matrix after 3 loops. So we go on to the next loop. Again, looking at our previous matrix, we want to analyze the third column and the third row. Now in our updated matrix, what would that look like? This 1 and this 1 intersect at a 0. So let's update that 0 in our next loop. They also intersect here and here. So those zeros become 1s. We don't update these 3 zeros, even though they intersect at 2 1s, because we're currently working on that row. Okay, finally, after k equal to 4 loops, I'm gonna copy this matrix down. We're going to analyze the final row and final column. And looking at those two, it looks like our final matrix will simply be entirely full of 1s. Go on to part B. We're given this relation right here, and I've already copied down the original matrix. So let's see what this looks like after 1 loop of Warshaw's. We have the first column and the first row, and it looks like the first row is full of zeros, so we're not going to update anything on the first loop. Therefore, after k equal to 1 loops, this is what our matrix looks like. Now, after 2 loops, what does it look like after 2 loops? Look at the second column and the second row. We have a second column full of zeros, so again, nothing happens. We go on to the third loop. Looking at the third loop now, we're looking at the third column and the third row. We see 2 1s right here intersecting at this 0. Let's turn that into a 1. We see that this 0 becomes a 1 as well. Okay, finally, we're on to our final loop now. Let's copy the previous matrix down. Looking at this final matrix, the 4th column, 4th row, it looks like the only 2 values that will be updated with new transitive relations will be this 0, and this 0. And we're finished. This is what the matrix looks like with all the possible transitive relations added. We see here that we have 1 column that is full of zeros. Sometimes it'll look like that. That's okay. It's still transitive, and this is the solution. Are these following relations equivalence relations? It's an equivalence relation if it is reflexive, symmetric, and transitive. So if it's all 3 of those properties, then the relation is an equivalence relation. So this first one is very simple. 0, 0, 1, 1, 2, 2, and 3, 3 pairings. And we're given the set 0 through 3. Is it reflexive? Yes. Right, it has all three, or all four of the elements reflexive on each other. Is it symmetric? Yes as well. We don't even have any values to test for symmetry, so we don't have like 1, 2 to test if 2, 1 even exists, so it is symmetric. Finally, is it transitive? Yes, it is transitive, right? We don't even have any transitive pairings to test, so it must be transitive. So because it passes all three checks, we would say that it is an equivalence relation. Next, part B. It would not be reflexive. And therefore, it would not be an equivalence relation. Right? And you know that because it doesn't have the pairing 1, 1 anywhere, just as a counterexample. And for C, it is reflexive because we have 0, 0, 1, 1, 2, 2, 3, 3. It is symmetric because we have the pairing 1, 2, and we have the reverse pairing 2, 1, both in a relationship. That's the only pairing we have to test. So it is symmetric. Finally, it is transitive. We have 1, 2, we have 2, 1, therefore we should have 1, 1, which we do. Looking at it backwards, you could say we have 2, 1, and we have 1, 2. That means we must have the pairing 2, 2, which we do. Therefore, it passes all three of the properties, and it is an equivalence relation. So looking at part B here, let's answer the tail end of the question. Determine the properties of an equivalence relation that the others lack. So this one, we've already said it's not reflexive. Is it symmetric? Well, it looks to be, right? So it has symmetry in all possible cases. Is it transitive? Well, we have the pairing 0, 2, and we have the pairing 2, 3, both in our relation. Do we also have the pairing 0, 3? Well, I don't see it, so it's not in there. Therefore, it's not transitive either. So this is not an equivalence relation because it lacks reflexivity and it lacks transitivity. Okay, now we need to determine whether the following relations on the set of people are equivalence relations. A and B are the same age. A and B are just any two people. Well, is it reflexive? Does it make sense to say A and A are the same age? Yes, it is. So it is reflexive. Is it symmetric? If A and B are the same age, then are B and A the same age? Yes, it is symmetric as well. Finally, if A and B are the same age, and B and C are the same age, then are A and C the same age? Yes as well, so it is transitive. Therefore, it is an equivalence relation. A and B have the same parent. Okay, so ask yourself, does A and A have the same parent or same parents? Yes, so it is reflexive. If A and B have the same parents, then does B and A have the same parents? Yes as well. If A and B have the same parents, and B and C have the same parents, then does A and C have the same parents? Yes. Two people with with three kids. So in that case, those three kids have the same two parents. So it would be transitive. Therefore, we would say yes, it is an equivalence relation. We go to part C. A and B share a common parent. So in that case, A and B might share the same father, but not the same mother, or the same mother, but not the same father. And I'll give you an example. Actually, no, I won't give you an example. I think that makes sense. Okay, so is it reflexive? Does A and A share a common parent? Yes, A and A must share the same parent. So, therefore, it is reflexive. Is it symmetric? A and B share a common parent, therefore B and A share a common parent too. Yes. Is it transitive though? The answer is no, right? Let's say there are three different people, A, B, and C. A and B might have a common parent. B and C might have a common parent, but that does not necessarily mean that A and C share a common parent as well. We would say, no, this relation is not an equivalence relation. Which subsets are partitions? Now, a partition is basically, or a partition into subsets, basically means that the subsets should contain all of the values of the original set. So the union of all of the subsets should equal the original set. Now also, in the definition of a partition, it must be that none of the sets overlap. So what that means is none of the subsets share any of the same values. So for example, two subsets could not share 3 because then it would not be a partition. Okay, so with that understanding, is A a partition? Well, let's look at it more carefully. We have -3, so that's checked. -1, 1, 3. Then in the second subset, we have -2, 0, and 2. So each of the elements in the original set are contained in these subsets, and these subsets do not overlap in any way. So therefore, we would say yes, A is a partition of the original subset, or the original set. Okay, part B. Well, this would not be a partition. Can you see why? Right, so it's not disjoint. What that means is 0 is shared in both of these subsets. It's not disjoint, so therefore it is not a partition of the original set. Okay, part C. We have 4 different subsets now. -3 and 3, so those are handled. -2 and 2. -1 and 1. Finally, 0. Well, all of the elements are handled in by the union of these 4 subsets, and none of the elements are repeated across subsets. So therefore, it is a partition. Part D. We have -3, -2, 2, and 3 in our first subset, and we have -1 and 1 in our second subset. Okay, so would this be a partition? Well, we have -3, -2, +2, 3, -1, and 1. But we do not see 0 anywhere here. So the union of these subsets does not equal the original subset because we're missing an element. We're missing the element 0. Therefore, no, D would not be a partition. Okay, hope you enjoyed this recitation.